Hi everyone, I'm Jarryd Martin and I'm presenting count-based exploration in feature space for reinforcement learning, which is work that I did with Suraj Narayanan, Tom Everitt and Marcus Huda at the Research School of Computer Science at the Australian National University. I'll be presenting a new exploration method that is compatible with any value-based RL algorithm that uses linear function approximation to approximate the value function. So the problem we address in this work is the exploration-exploitation dilemma. I'll assume that most people here have quite some familiarity with this problem, but for completeness, the exploration-exploitation dilemma is a problem faced by every RL agent when it needs to trade off its desire to greedily gain reward in the short term based on the information it currently has about the environment and its need to forgo some short-term reward in order to gather more information about the environment, thereby reducing its uncertainty and thereby making sure that it is going to maximize its reward in the long term. Now, efficient exploration is fairly well understood in small MDPs for which tabular methods are appropriate, but it is very much still an open problem in domains with large state spaces, which make exploration very hard because there's just a lot more to explore, and particularly in environments with sparse rewards. If rewards are very dense, even in very large state spaces, the agent can in some sense be guided by the collection of reward to explore the state space in a roughly efficient way. But if this isn't the case, the agent needs a principled way of exploring the environment efficiently, even in the total absence of the reward during large parts of training. What we have pictured here on the screen is a good example of this sort of environment. It's Montezuma's Revenge, a game from the arcade learning environment, which has recently become a popular testbed for reinforcement learning algorithms. And in this game, the agent needs to explore a large map of rooms efficiently in which there are only a couple of rewards in a few rooms. Now, what's the current state of the art? How do algorithms that succeed in these domains explore the environment efficiently? Roughly, they tend, for the most part, to encourage the agent to visit novel states in order to maximally reduce its uncertainty about the environment. It's important to note that it's not sufficient to just keep track of an empirical visit count of all the states that the agent has visited before. This is because in these very large domains, the agent is likely to only visit a tiny fraction of the state space during training. This means that during and after training, most states have a visit count of 0, always. This means that when an agent is confronted with a choice between visiting two states, most of the time, both of these states will have visit count 0. And what this means is that the agent is left without any tools for deciding which of these would be better to explore or which would reduce its uncertainty more. Now, this is frustrating intuitively because even if we haven't visited either of these two states, one of them might be much more similar to the states that we have visited in the past, and one might have really quite novel features compared to the ones that we haven't visited that we've visited in the past, the states in the history, rather. Which means that we don't want to just encourage our agent to visit novel states in the sense of unvisited states. We want to especially encourage the agent to visit states that have novel features with respect to the ones in the history. And the high-level way of describing this approach is that we want to make a curious agent, an agent that's curious about states that have novel features. In order to do this, what we need is a feature representation psi of the state space that is appropriate for measuring the similarity of states to the ones in the history. Once we have this feature representation, we can use it to compute some approximation to the empirical visit count or some analogous quantity which measures novelty, which is sometimes in the literature called a pseudocount, n hat, and we'll continue to refer to it as such for simplicity. Now, this pseudocount should be high if the state shares few features with those in the history, and should be low if the state has quite a lot of features that have been encountered a lot of times before in visited states. Once we have this pseudocount, this measure of novelty, what we can do is compute a novelty-based exploration bonus. So you can see from the expression there, the important thing to note is that the exploration bonus depends on the inverse square root of this pseudocount, of this novelty measure, which means that if the pseudocount is very low, the exploration bonus will be very high. So the exploration bonus is high for states with novel features. So how can we use this exploration bonus for reinforcement learning? All we do is add the bonus to the normal reward R and train the agent on the augmented reward, which is this R plus the exploration bonus. Now, what we have here is a graphical representation of the sorts of algorithms I've been describing on the previous slide. Down the bottom, for your reference, I have three examples of the three of the most empirically successful algorithms that implement this principle and roughly use the architecture I'm about to describe in this graph. These all perform very well on the arcade learning environment in hard exploration games. So it seems like a promising approach in general. What we have represented on the top row up here is something like a standard TD learning algorithm, a value-based reinforcement learning algorithm, which takes in a state action pair, transforms that into a feature representation that has been specifically designed or learnt for representing the value function, a feature representation for value, phi. This feature representation is then used to estimate the value of that state action pair, and that Q value comes out the other side. What these algorithms listed down the bottom add to the standard picture, or the standard architecture, is firstly a separate feature representation, this time not for representing value, but for representing novelty. Because what we want is a feature representation in which to measure the similarity of this new state action pair to those visited in the past. We call this feature representation psi in this graph. That feature representation goes into some part of the algorithm which estimates novelty, computes an exploration bonus, and then adds it to the reward. This goes into the value estimator, and the augmented value of this state is estimated. And so you can see that an agent that is going to maximize or estimate this value function, this augmented value function, and then act greedily with respect to it, is going to, in some sense, elegantly trade off its desire to get rewards and to explore novel states. The difficulty when we think about applying or extending these algorithms is that all three of them use different feature representations for novelty. And the natural question arises, which of them is actually more appropriate for measuring the novelty of a state? The difficulty is that none of these justify their choices theoretically. So all we are left with is quite similar, although very good, results on empirical benchmarks. What we wanted to do in this work was to see if we could derive a more principled way of choosing a feature representation in which to measure the novelty of unseen states for efficient exploration. Now, to get some intuitions about this, we're going to take a toy example here. What we got represented here is an agent. In the center, this goggly-eyed robot, and up the top we have the agent's memory of the restaurants it's visited. I should say that what this agent cares about, its goal, its value function, is having great dining experiences. And represented up the top are all of the restaurants that this agent has been to in the past. So as you can see, the agent is a fan of McDonald's. Most of the nights on which it's previously gone out for dinner, it's been to a McDonald's. It's had a couple of excursions into other fast food chains, but mostly it's very loyal. It's the kind of agent who likes going around the city and detecting the little similarities and differences between the McDonald's, let's say. All the McDonald's in its city. Now, I should say something more specific about this agent's value function. When it goes out for dinner, it doesn't care about the service, it doesn't care about the ambience, it doesn't care about the location or how long it takes to get to the restaurant. What this agent cares about are the food and drinks. We could say that the only two components of its value function are the flavors and the variety on the drinks menu. And so, tonight, the agent has decided it wants to expand its current culinary horizons. It wants to explore the space of possible dining experiences a bit better. And in short, it's decided to explore tonight. Now, what we have here is the agent's choice as it currently stands. It's narrowed it down to two options. What we've got on the right is another McDonald's. Importantly, a McDonald's the agent has not been to before, but indeed another McDonald's. On the left, we have an Indian restaurant, Tandoori Dhaba, which the agent has also not been to. Now, in order to determine which of these states would be more novel or more worth exploring, the agent has listed the relevant features. It's noticed that the McDonald's is likely to have the same flavors as most of the restaurants that it has visited in the past, and the same drinks menu too. It's also correctly identified that the Indian restaurant is likely to have very different flavors from anything it's experienced in the history, and indeed also a very different drinks menu. It's important to note that the agent has never ever been to an Indian restaurant or even a restaurant that wasn't a fast food chain. So it's obvious to us when looking at this which restaurant the agent should consider to be more novel or more worth exploring. It's obvious to us intuitively which of these choices would give the agent more information about the space of possible dining experiences. Going to just another McDonald's may not actually tell it that much more about what it could be experiencing in the world of food. This is because we've made this comparison with respect to the features the agent actually cares about when deciding on dining experiences. It cares about flavors, it cares about the drinks menu. The McDonald's has pretty much similar flavors and drinks menu to everything experienced in the past, so it's not that new. But it's important to note that this is the case even though there are many, many features in which this McDonald's might actually be novel, in the sense that there are many, many features this McDonald's might have which are very different from the McDonald's that it's previously visited in the history. Let's consider, for instance, that this McDonald's is in a heritage building. I'm sure you've seen this, these beautiful buildings that have in some sense been taken over by a McDonald's. So it might be the case that this McDonald's has extremely different wallpaper to all of the McDonald's that it's been in before. It has a very different parking setup. It might have old chandeliers retained from the old heritage building, so the lighting in this McDonald's is very, very different to all of the ones in the past. It might be much more luxurious and grand and large, so the floor space of this McDonald's might be orders of magnitude larger than all the previous McDonald's that this agent has ever visited before. Now, we could even take this analogy further and say that this Indian restaurant on the left, in fact, took over its location from a failed McDonald's. And so we could say that in these features, wallpaper, parking, floor space, lighting, this Indian restaurant happens to be indeed more similar to the McDonald's that the agent has visited in the past. But what we should note from this example is it doesn't matter whether or not the McDonald's is less novel in these irrelevant features, and the McDonald's is more novel in these irrelevant features, I could say, and whether the Indian restaurant is less novel in these irrelevant features. With respect to the features that matter, the Indian restaurant is clearly more new. Which are the features that matter? Well, from this example, it seems intuitive that the features that matter are the ones that are relevant for determining value. Value-relevant features are the features that are relevant for measuring novelty. Now, when we return to these architectures, it's clear that the strangeness of this setup, I hope, should appear clear. These architectures construct a feature representation for novelty that is totally ad hoc and seems to have nothing necessarily to do with the features that are relevant for determining value. Of course, they may by chance coincide with the features that are relevant for determining value, but there seems to be no structural reason why this should be so or should be guaranteed to be so. So now the question becomes not just which features are relevant for determining novelty, but instead, which features are relevant for determining value. And to us, the natural answer seems to be the features which are relevant for determining value for the agent are the features that are already being used to represent the value function. Indeed, if these features weren't relevant to representing value in this environment, they probably wouldn't allow for a good approximation to the true value function. So, this motivates our architecture for our algorithm, which is called the phi-Exploration-Bonus algorithm. It takes a state action pair and puts it through a single feature representation designed or learned for representing value, and then passes this same feature representation to a value estimator and to a novelty estimator. The important thing to emphasize is that novelty here is evaluated with respect to the same features that are used to estimate value. This has some immediate advantages, obvious from this graph, that we don't need to design or learn an entirely separate ad hoc feature representation just for exploration, just for estimating novelty. That makes our phi-Exploration-Bonus algorithm simpler and less computationally expensive than previous approaches. We also consider, however, based on the intuitions that I tried to capture in the example on the previous slide with our dining robot, that this is also a more principled way to extend novelty-based exploration to the large state space case. Now, for completeness, the algorithm is listed here on this slide, which these slides will be online and you can refer to them later. For now, in my remaining time, I'll just describe some of the empirical results we had when implementing this exploration bonus method in the arcade learning environment, I should say. So what I've pictured here are the results from just 2 of the games. We tested it on more games than this, but these 2 games really draw out the effectiveness of this method. And they are indeed 2 of the hardest exploration games in the arcade learning environment. They're 2 games, for example, which Deep Q networks with just epsilon greedy exploration is unable to even score. Certainly in the case of Montezuma's Revenge. What we have here listed here in this table, the first row is our algorithm, the phi-Exploration-Bonus method, implemented with SASA, with linear functional approximation. The second row is the same SASA algorithm, but with standard epsilon greedy exploration. What we have next are double DQN with pseudocount, an algorithm from Google DeepMind from 2016. And the other algorithms below you can refer to in the references. But these are all algorithms that roughly use the same architecture that I've described early on in this talk, which we deviate from by using the same feature representation for exploration and for value estimation. The plots up the top show the controlled experiments we've done comparing our phi-Exploration-Bonus method's efficiency to that of epsilon greedy exploration. And what you can see is that the SASA agent with epsilon greedy exploration in Montezuma's Revenge converges to a very poor score almost immediately. And indeed, our observations show that this agent rarely even manages to leave the first room in the Montezuma's Revenge pyramid. Our phi-Exploration-Bonus agent continues to improve throughout training and actually manages to explore about 14 or 15 rooms, which to the best of our knowledge is certainly equal to the most explored by any non-linear or non-linear learner to date. The score on the right, we have the same results in Venture, and the epsilon greedy agent actually fails to score at all, whereas the phi-Exploration-Bonus agent continues to improve throughout training and explore a much larger part of the map. Venture is also a large map-based game with smaller rooms. Now, the important thing to note about the table of results here below is that Montezuma's Revenge, the score in Montezuma's Revenge, we believe, is indeed the second highest ever reported for any linear or non-linear learner, and the score in Venture, we believe, is the third highest, to the best of our knowledge, ever reported. In a particularly nice thing that we were able to observe was that the phi-Exploration-Bonus method was with the SASA as our reinforcement learning algorithm was indeed the only algorithm to achieve near state-of-the-art scores in both these games. That's the only algorithm ever reported to date to do so, which suggests that the phi-Exploration-Bonus method is able to produce good results and indeed efficient exploration across a range of sparse reward, large state space, hard exploration games. And what we have in brackets next to the names of each algorithm are the training times in millions of screen frames. So it's important to note that the phi-Exploration-Bonus algorithm achieves these scores and does well in actually half the training time of the bottom 2 algorithms referred to there. So that's also a nice thing in the sense that not only did it perform well and achieve near state-of-the-art scores, but it did so in modest training times compared to some of the other competitive algorithms. Now, that's all I'd like to go through here. If it's possible, it would be, and people are interested, it would be fantastic if the video of our agent playing the Atari games could be played now. If not, it's available online. Feel free to refer to it by searching for my name or those of my collaborators. And here I just have the references for completeness, which are mostly references to those other algorithms I described earlier in the talk. Thank you very much for your attention, and I wish you all well at the workshop. Very sorry not to be able to be there in person. Thanks for your attention again. See you later.